All right, let's go ahead and start our next unit on solutions. Start off with an introduction. Remember that a solution is a homogeneous mixture. Homogeneous mixture has components that are too small to distinguish, has a uniform composition, and so it's made up of solvent and solute. We call the components of that mixture. So maybe a little different definition of solvent and solute than you're used to. The solvent is the component present in the larger quantity, usually, or from last year, probably recall the solvent as being the substance that is doing the dissolving. And the solute is the component present usually in the smaller quantity or smaller amounts, or it is the substance that is being dissolved. It gets a little bit tricky when you mix, say, two liquids. Which one is the solute, which one is the solvent, and that's why first part of those definitions is useful. All right, solution could consist of a mixture of any states of matter. So for example, you could have a solid dissolved in a liquid, so you could have, say, sugar dissolved in water. This would give a homogeneous mixture. That's a solution. You could put a liquid dissolved in a liquid, like alcohol, like ethanol, in water. Both ethanol and water are liquids. Mix those together, you get a solution. Could have a gas in a liquid, could have a gas in a gas. So air is a homogeneous mixture of gases. We'll see later on when a solute is added to a pure liquid, it will change the properties of that liquid. This is known as colligative properties. Change of properties such as boiling point or freezing point or osmotic pressure. So that'll be later. All right, two factors that will determine if a solution or form. So the dissolving process is known as dissolution. So if you see that term dissolution, it just means dissolving. Dissolution processes are favored, meaning more likely to occur if, letter A there, a decrease in energy of the system occurs. So remember, if the total energy of the system decreases, this is due to the fact that that process is exothermic. In an exothermic process, delta H is negative. So for any dissolving process that is exothermic, it is likely to occur spontaneously or is thermodynamically favored. That's a term that we'll use when we get to thermodynamics. Or dissolving process is favored or likely to occur spontaneously if there is an increase in the disorder or entropy of the system. This is also a thermodynamic concept. Solutions are mixtures, so this value is always increasing when a solution forms. So you take two, say, pure substances, you combine them, what you end up with has a higher degree of disorder or entropy, and so entropy is always increasing when solutions are made. So let's look more closely at the dissolving process. And we're going to look at a couple different situations. First one here is dissolving of a solid solute into a liquid solvent, say sugar in water or salts in water. We'll start with this though. True or false, all chemical processes require energy? Go ahead and answer that question. I think we've talked about this before. That is true. All chemical processes require energy. Even an exothermic process requires energy? Certainly does. I'll show you that in a bit. Next question, true or false? All chemical processes release energy. Go ahead and answer that. That one is also true. Well, even in an endothermic process, energy is released? Absolutely. So what determines if a process, a chemical process, is endothermic or exothermic? Has to do with the magnitude of the energy that is required compared to the energy that is released. So let's take a look. The heat of solution, delta H solution there, heat of solution is what we say, which is the energy required or released, depending if it's endothermic or exothermic, when a substance dissolves. So heat of solution for a solid dissolving into a liquid may be viewed as a three-step process. All right, let's start off with the processes within that entire process that are endothermic. Now, all of this, even though we're going to break it up into steps, all of this occurs kind of simultaneously. So first step is separating solute particles from one another. Make a note, this is called expanding the solute. So let's say that you take sodium chloride and you put it in water. Well, in order for the sodium chloride to dissolve, you need to separate the sodium ions from the chloride ions. So you have to break the attractive forces between the particles that make up that solute. So remember, breaking attractive forces requires energy. So specifically, if our solute is an ionic solute, the energy needed for this process is equal to the crystal lattice energy. So we're breaking ionic bonds. Another part of the process that requires energy is separating these solvent particles from one another. This is known as expanding the solvent. In order for water to separate the Na plus from the Cl minus, the water molecules need to separate from one another so they can grab onto those ions. If the solvent happens to be water, the energy needed to separate those solvent particles from one another is the energy needed to break the hydrogen bonds. So we're talking about breaking intermolecular forces, in this case specifically hydrogen bonding if the solvent is water. So those are the processes that require energy. Of course, we have processes that release energy. Remember, in general, when attractive forces form, energy is released. So it says solute and solvent particles come together. So attractive forces form between solutes and solvents. Energy is released during this process, and the energy that is released during this process is known as solvation energy. More specifically, if the solvent is water, this is called hydration energy. So either one of those, energy released when attractive forces form between solutes and solvent particles. All right, so what determines if the dissolving process or heat of solution is endothermic or exothermic? Depends on, as I said, magnitude of the energy required compared to the energy released. So number 3, it says if the solute solvent attractive forces are greater or stronger than the solute and solvent attractive forces, then the heat of solution, the delta H for the dissolving of that substance, is negative. Remember, negative delta H means exothermic. So let me restate that. If more energy is released when the solute-solvent interactions form than what is required to break apart solute-solute and solvent-solvent attractive forces, then the process will be exothermic. So a good example of this would be heat packs. In a heat pack, you have calcium chloride, and the calcium chloride, not in all heat packs, but in some of them, the calcium chloride dissolves in water. The dissolving of calcium chloride gives off heat. This is an exothermic process, so it heats up. So that would be an example of an exothermic dissolution process. Other way around, if the solute-solvent attractive forces are smaller or weaker than the solute-solute and solvent-solvent attractive forces, then the heat of solution for that solution is positive, or the dissolving process is endothermic. If more energy is required to break apart the solute-solute and solvent-solvent attractive forces than is released when solute-solvent attractive forces form, then overall that process is going to be endothermic. So an example of this, of course, would be an ice pack. In ice packs, oftentimes it is ammonium nitrate. And the ammonium nitrate is dissolving in water. The dissolving of ammonium nitrate is endothermic. When ammonium nitrate dissolves, it makes the water colder. Now, if you take a look on page 502 in your book, kind of a Born-Haber type diagram where we show energy required and energy released. And so we see energy is required to break apart the solvent particles from each other and the solute particles from one another. So that's step A and step B. And then those solute solvent particles exhibit attractions towards each other, and the formation of those attractive forces releases energy. So notice that step C is greater than the sum of steps A and B, meaning more energy is released than is required. Therefore, the dissolving of that substance would be exothermic, and delta H is negative. Now, be aware that polar solvents like water will dissolve polar solutes and ionic solutes. So ionic solutes will only dissolve in a polar solvent, something that has opposite ends that can grab onto the positive and negative ions of that solid crystal. Whereas nonpolar solvents will only dissolve nonpolar solutes. So we use the solubility rules to predict if ionic substances will dissolve in water. But what if you have molecular substances? How do we predict if some molecular substance will dissolve in another molecular substance? We use the expression like dissolves like, meaning polar in polar, nonpolar in nonpolar. If you take a look on page 504, it shows the dissolving process for sodium chloride. Again, those opposite ends of the water molecules are attracted to the chloride and sodium ions. And notice how those ions, water molecules, interact with one another. On the margin, on the bottom, we have naphthalene, which is nonpolar. And it has nothing that could grab onto, say, the sodium ions and the chloride ions. So sodium chloride would not dissolve in naphthalene. All right, two factors that affect the energy released when attractive forces form between solvent particles and ions. So water molecules and ions like shown in that diagram. Of course, we're talking about Coulomb's law. Anytime we're talking about attractive forces between charged particles, we use Coulomb's law. So the greater the magnitude of charge of the ion, the more energy released when those attractive forces form between solute and solvent. And then the size of the ion, of course, also affects the energy released. So the smaller the ion, the stronger the attractions between the ion and the, say, water molecule. And so just be aware that both size of the ion and magnitude of charge affects the hydration energy. In fact, take a look at an example of this on page 505. We have some cations and anions, gives us the ionic radii of those ions. Actually, it's just cations here. And the charge to radius ratio, it's called. So it gives us an idea of, what's a bigger factor, the charge or the ionic radius. And then we see hydration energy. Notice it's negative, meaning exothermic. So the bigger the magnitude of that negative, the more energy is released. So K plus, Na plus, Li plus, magnitude of charge is the same, but size decreases as you go from K plus to Na plus to Li plus. And notice what happens to the hydration energy. It increases as you go from K plus to Na plus to Li plus. If we go all the way to the bottom, we have aluminum, has the greatest magnitude of charge. And we see there that the hydration energy is the greatest of all the substances listed in that table. So very important. Make sure you take a look closely at that table. All right, how about dissolving a liquid into another liquid? This process, by the way, we talk about liquids dissolving in other liquids, is called miscibility. Two liquids that dissolve in one another are said to be miscible. Two liquids that do not dissolve in one another, like oil and water, are immiscible. So the factors listed for solid solutes apply to liquid solutes as well. However, the attraction between liquid particles is usually much less. Remember, we talked about the difference between solids and liquids, and the difference being the strength of the attraction between the particles. And because the attraction between liquid particles is less than between solid particles, there's a greater probability that the heat of solution will be negative. So it's easier to break apart those solute particles from one another. So that means that less energy total is required maybe, and therefore more likely that overall the process will be exothermic. Take a look on page 506. We see what I just talked about, immiscible substances. And so we see oil and water. And then we also see an example next to that, figure 14.3. Looks like we have methanol there, CH3OH. Methanol and water, both methanol and water are liquids, and they dissolve in one another because they're both polar. Like dissolves like. All right, what about gases dissolving in water? This may occur if several things are true. One, the gas is capable of hydrogen bonding with the water. So we would see an example of this with hydrogen fluoride gas. So hydrogen fluoride exhibits hydrogen bonding with each other, also would form hydrogen bonds with water molecules as well. Or if the gas dissociates in water, such as the strong acids, so hydrogen chloride will dissolve in water and it will dissociate into H plus and Cl minus ions. Or a gas may dissolve in water if it actually reacts with the water. For example, carbon dioxide reacts with water to produce carbonic acid. And so those are kind of the ways we can determine if a gas dissolves in water. One of those three ways. All right, next up we have rates of dissolving. So how fast, the time it takes for a solute to dissolve into solution, and saturation. These are two totally different things, even though they're listed together in the notes. It says solid solutes will dissolve into liquids more rapidly if the solute is crushed into a powder. This occurs because more of these solute particles will come in contact with the solvent particles. So when we get to kinetics, we'll talk about the factors that affect the rate of a chemical reaction. This is not a chemical reaction, but the same principle applies. If the solute solvent particles come into contact with each other more, then that solute will dissolve faster. So for example, if you take a sugar cube and put it in water, only the surface or outside of the sugar cube is in contact with the water, and thus only the outside will dissolve. But if you take that sugar cube and you break it up into smaller pieces, you're exposing more of that substance to the solvent. There's going to be more collisions between solvent and solute particles, and this will then allow the solute to dissolve faster. So by crushing a solid, you are increasing its surface area. Powders, of course, kind of the form of a solid that has the greatest surface area. We're talking surface area to volume ratio. All right, on to saturation. Unsaturated. An unsaturated solution is a solution that contains less than the maximum amount of solute dissolved. Or as it says in the notes, a solution that could hold or could dissolve more solutes at that particular temperature, or because it has less than the maximum dissolved. Saturated solution, of course, then, is a solution where it contains the maximum amount of solute dissolved. No more solute will dissolve because the maximum amount is already dissolved. So macroscopically, a saturated solution, macroscopically meaning what we can see with our eyes, if it's saturated, we'll see that no more solute is able to dissolve. If you put more solutes in a saturated solution, that extra solutes will not dissolve. They'll just sink to the bottom and sit there. At the particulate level, you have a saturated solution when the rate of dissolving is equal to the rate of the opposite of dissolving, which is crystallization. So dissolving is going from solid, let's say, to aqueous. Crystallization is going from aqueous to solid. It is possible, though it just doesn't happen by itself, to have what's called a supersaturated solution. In a supersaturated solution, there is more solutes than what can normally dissolve at that particular temperature. So a solution that contains more than the maximum amounts of solutes dissolved in a solution. Take a look on page 509. It's a common demonstration in chemistry. This is sodium acetate. If you take a supersaturated solution of sodium acetate and pour it out, you'll get the extra solutes that was dissolved to come out of solution. We call this a sodium acetate tower. Hopefully your Chem 1 teacher showed you a demonstration of a supersaturated solution, much like what's shown in the picture in the margin there. So some other factors besides surface area of the solute that affects the rate of dissolving is temperature. Now there's a couple different things here. So the higher the temperature, and this is not in the notes, the higher the temperature, the higher the rate of dissolving. Again, those particles are moving faster, they're colliding with each other more frequently. This is going to lead to a higher rate. The degree of the amount of solute that can dissolve, this is called solubility, how much can dissolve, is also affected by temperature. Solutes where the heat of solution is positive, we're talking about an endothermic dissolution process, will be more soluble at a higher temperature. So think about something like, I don't know, potassium nitrate. The dissolving of potassium nitrate is endothermic. And so kind of thinking back to Le Chatelier's principle, if you increase the temperature, this is going to allow more of the solid to dissolve. We're going to push that over, even though it's not an equilibrium system per se. We're going to push this all the way over to the right, so more solid will dissolve. Conversely, solutes where the heat of solution is negative, or an exothermic dissolution process, will be more soluble at a lower temperature. So the dissolving of sodium hydroxide, for example, is exothermic. And you could dissolve more sodium hydroxide in cold water than you can in hot water. Take a look on page 510 in your textbook. Hopefully that's familiar. That's called a solubility curve graph. What this shows is the relationship between solubility. Remember, solubility refers to the amount of that substance. It has nothing to do with rate, so be careful. The amount of the substance that can dissolve. Notice it's per 100 grams of water versus temperature of the water. And so for most of the substances there, we see that they have a positive slope, which means that they are more soluble at higher temperatures, or the dissolving of those substances is endothermic. Sodium chloride is pretty flat, meaning its solubility is not really affected by temperature. And then we got some weird stuff going on there with the sodium sulfates. It increases to a certain point and then it starts to decrease. Something else to keep in mind, the solubilities of most solid solutes increase with increased solvent temperatures, but this is the opposite for gases. Gaseous solutes are less soluble at higher solvent temperatures. For example, you can dissolve less hydrogen chloride gas in hot water than you can in cold water. So just be aware that the trend for or relationship between solubility and temperature is different for solid solutes than it is gaseous solutes. In fact, another factor that affects the solubility of gaseous solutes is pressure. And we're going to look at something called Henry's law. What Henry's law shows is that the solubility of a gas in a liquid is directly proportional to the pressure of that gas above the liquid. So here's our equation, and we'll identify the variables. So Cg is the concentration of the gas. The concentration of the dissolved gas, so how much is actually dissolved in solution. This could be measured in molarity or even mole fraction. We'll review what mole fraction is in just a bit. So it could be either one of those. Or it could be solubility. So solubility refers to the amount that is dissolved. That's fine there as well. K is a constant, it's a proportionality constant. And then P gas, of course, is the pressure of the gas. Again, this is pressure of the gas above the liquid. So we see as the pressure of the gas, let's say, increases, then the amount of the gas dissolved in solution will also increase, leading to a higher concentration. In fact, this is how Coca-Cola and PepsiCo gets the carbon dioxide to dissolve in water. Carbon dioxide is nonpolar, does not like to dissolve in water, but we can get it to dissolve in water by taking that carbon dioxide under high pressure and kind of pushing it, forcing it into the water. So I just mentioned concentration. In fact, we can express the concentration of a solution several different ways. Hopefully this is review. The most common way of expressing the concentration of a solution is molarity. With all of these, what they have in common is they are all ratios. So for molarity is a ratio of moles of solute. Make sure you label that, please. I'm just going to write it like this, but moles of solute per liter of solution. In fact, I think I'm going to write it out too, just so you know exactly what it is. Moles of solutes, so the amount of the solute in moles per liter of solution, the volume of the solution after the solute has been dissolved. Big M is a symbol. Molality, the symbol is lowercase italicized m. So I try to find a font that would work for that. So when I write, I just kind of write a cursive M. So molality, like molarity, is also a ratio. It is a ratio of moles of solutes, this time though, per kilogram of solvent. So per mass of the solvent in kilograms. Mole fraction, we're talking about gases. The mole fraction of a gas is a ratio of moles. Moles of, and it could go either way, solutes or solvents. So depending if you are determining the mole fraction of the solutes versus the mole fraction of the solvents. Later on, we'll do some calculations where we're actually using the mole fraction of the solvent. So it can go either way. Mole fraction of one of the components of the mixture over the total moles of those substances. And then mass percentage, of course, is just, there's no symbol for that one. Mass of one component of that mixture over the total mass. So it's kind of like mole fraction, except for mole fraction, we leave it as a decimal. For mass percentage, we multiply by 100 to get a percent. A few examples of solution concentration, starting with 14.1 on page 513. What is the molality of a solution that contains 128 grams of methanol in 108 grams of water? So now technically how this is worded, the methanol is the solute and the water is the solvent. Though we said earlier that the solute is usually the component present in a smaller quantity. So we're going to ignore that here, this little weird one. So the methanol is the solute, the water is the solvent. So we need to take that 128 grams of methanol, convert that to moles, take the 108 grams of water and convert that to kilograms and divide those, and we get a concentration of 37.0 molal. All right, let's try one on your own, page 540. Number 27, it asks to calculate the molality, but it gives you the density of the solution, and with that we can determine then the molarity. So go ahead and calculate the molarity of the solution too. Go ahead and pause the video now. All right, so let's use the density to find the mass of the solution, and then we use the percent composition. It's 32% by mass urea. And that'll give us the mass of urea in 1,000 milliliters, or in 1 liter. And then we'll take that mass and convert to moles. And that is per our 1 liter. Get a concentration of 5.80 molar. All right, 514, example 14.3. This time we're doing mole fraction, so we're given the mass of the two components of that mixture in the previous problem. Take those, convert each of them to moles. We already did one of them in the previous problem. So convert both to moles, add them up, divide moles of one by the total moles, and we get our mole fraction, which again is kind of like a percent. So 0.400 for the methanol, 0.600 for the water. All right, practice problem number 29 on page 540. Please do A, B, and C. Pause the video now, please. Oh, we need to go back to the answers. Sorry about that. So here's the setup for number 27. So I use the percent by mass, 32% urea. So that's 32 grams per 100 grams of solution. So I took the 32 grams of urea, convert to moles, and then the rest of the 100 grams, that's not urea, which would be 68 grams, is water. And so just using 68 grams, convert that to kilograms, and we divide those to get the molality. All right, sorry about that. Go ahead and do number 29 now. So here are three setups. We got mass percentage, mole fraction, and molality. All right, so that concludes this lesson. I'll give you some practice in just a bit. Thanks for watching.